Okay, then in the final example, I'm going to look at a problem similar to the third problem in the previous video. In that problem, we had integral secant square of x times tangent x plus 3 dx. And the answer in the previous problem was 1/2 tan x plus 3 quantity squared plus c. Now if you notice, the new integral that we're comparing that to is really just 2 times that. So I guess we're going to expect the second integral, to be twice the first one. So we're expecting an answer of tan x plus 3 quantity squared plus c. And let's see if we get that using u substitution. So we let u equal tan x plus 3. And here we need 2 secant square x dx. So we could actually multiply both sides by 2. And so now we have that 2 du is equal to 2 secant square x dx. And tan x plus 3 is still equal to u. And so now we have 2 integral u du, which is 2 times 1/2 u to the second plus c. And the 2 and the 1/2 will cancel, and we'll end up with just u squared plus c, which is tan x plus 3 quantity squared plus c. So these three problems show a slight variation on the method we used in the previous three problems. And here we didn't get an exact match, but the match that we got when we found the derivative of the inside function was a constant multiple of what was on the outside, and so that's going to work. I'll continue with 2 more examples. And the first one is just a simple function composition integral. We don't have anything on the outside, but it's okay because the derivative of the inside function is really just 2, and so that is a constant multiple of whatever's on the outside, which is nothing. So there's no x on the outside, and we don't need to have an x. So I guess the moral of this story is that whenever you have an inside function whose derivative is a constant, you should always be able to do u substitution successfully with that. So we let u equals 2x minus 1, then du is going to be 2 dx. We're only trying to match up dx in the original integral, so I'm going to divide both sides by 2, so that now dx is equal to 1/2 du, and 2x minus 1 is u, and so we're going to get 1/2 integral u to the 1/2 du, and that is 1/2 times 2/3 u to the 3/2. When I multiply out the coefficients and I replace u, I get 1/3 times the quantity 2x minus 1 to the 3/2 plus c, and that's my final answer there. Now we're going to look at this same problem with a slight twist to it. Now in this case, we are not able to match the derivative of the derivative of the function on the inside does not match what's on the outside. And it's not just a constant multiple difference. Now there's a variable difference. So in some cases this will also work. You're going to have to kind of go through the steps here to see if it will. And we still let u equal 2x minus 1. And so du is equal to 2 dx. We can't use the x, but we can solve for dx. And we get 1/2 du is equal to dx. And of course 2x minus 1 is our u. And so if we consolidate what we have here, we would get 1/2 integral of x times u to the 1/2 du. And we can't go forward with this because we're integrating with respect to u, but we have an x variable in there. And so what we're going to have to try with this is to take our definition of u, and we're actually going to solve that for x. So we add 1 to both sides and divide by 2. And now we have something that, in terms of u, that we can swap out for x. And when we simplify that, we get, now you note we get that 1/4 comes out. You notice that the u plus 1 and the u to the 1/2 can now be distributed. And when we do that, we do get an expression that's entirely in terms of u and that are all powers of u. And when I integrate the first term, I'm going to get 2/5 u to the 5/2. The second term, I'll get 2/3 u to the 3/2. And with the first term, I'll get 2x minus 1 to the 5/2 over 10, and 2x minus 1 to the 3/2 over 6 plus